I'm Minae, and I'll be talking about how we can use active learning to design negotiation agents. Negotiation is a bargaining process by which a joint decision is made by two parties. It's pretty important and shows up in a variety of situations like court, negotiating salaries, or conferences. But let's look at a more tangible example. My friend Bob and I are eating dim sum and need to come up with a way of splitting it. Depending on our constraints like allergies and preferences, we can agree on how to split the dim sum. There is no clear answer of what a fair split is, so we need to negotiate. This discussion is a decentralized process since there is no central authority, and it is partially observable since I do not know Bob's preferences a priori. Our goal is to develop an AI agent that can negotiate in tasks like these. So what kind of AI negotiators do we want? We definitely want agents that maximize their self-interest, but we also don't want to be too selfish. Otherwise, Bob and I will never reach an agreement. We define the fairness of an agreement using Pareto optimality. These objectives are often conflicting, and in this work, we look at how to design negotiation agents that can balance these two desiderata. So how do you do this? One way is to use supervised learning. We can collect a dataset, as shown on the left, and train a model to maximize the likelihood of utterances in that dataset, as well as the final split of items for each negotiation. One downside of this approach is that the model may inherit any biases that the dataset may have. For example, if friends are overly agreeable, the resulting model will be biased towards compromise. As another approach, you can directly design a reward function and use reinforcement learning to maximize your objectives. Here we have two negotiation agents, Alice and Bob, initialized with the supervised learning model. We keep Bob fixed to stabilize training, while Alice is going to be the RL agent. During training, Alice and Bob negotiate, where Alice's objective is to maximize her reward. Reinforcement learning inevitably will lead Alice to explore and generate out-of-distribution utterances that Bob, who is fixed, has never seen before. For instance, in practice, Alice can become very aggressive and badger the same aggressive proposal over and over again. Because these utterances are out of distribution for Bob, he cannot appropriately respond to Alice. Although one might expect RL to make Alice robust to dataset biases, she still inherits them through Bob, who is fixed, and by being trained on the static dataset, is still biased. To alleviate this problem, you can interleave RL and SL training, where SL acts as a regularizer to prevent Alice from going too out of distribution. However, similar issues persist in that you still get biases inherited from the dataset due to supervised learning. We see that a major problem with these approaches is that agents rely on possibly low quality and static datasets. Our key insight is to take an active learning approach. We unfreeze Bob and improve him with guidance from an expert. So in our framework, we have the same RL setup, but instead Bob does two things. He negotiates with Alice, but also scores each of Alice's utterances at the same time. The score is the log likelihood of Alice's utterances with respect to Bob's model. We then take the lowest or most surprising score and assign that as the overall score for that negotiation. After doing this for all training negotiations, we pick the 500 most novel negotiations, which are the negotiations with the lowest scores, and ask an expert to annotate them. We save the index of Alice's most novel utterance, and the expert starts negotiating with Alice from that point. We then update our dataset with these annotated negotiations, and then update Bob by training him on the new dataset. We then continue training Alice as before with the new Bob. The main question we wanted to answer in our evaluation is whether our approach can balance these two desiderata. To measure self-interest, we look at advantage, or the average difference between Alice and her partner's score over 5 training epochs, which is the x-axis. As expected, RL has high advantage and SL has low advantage. Our approach is closer to RL than RL plus SL. We can say that our approach does a good job of preserving self-interest. To assess how compromising agents were, we looked at Pareto optimality and the agreement rate. The graph looks flipped, but our approach is able to maintain higher scores than RL. We can say that our approach balances self-interest and Pareto optimality the best. If we look at the novelty of Alice's utterances under each model, we see that ours is the most novel, suggesting that Alice's novel utterances is what potentially allowed her to balance both desiderata. We conducted the same study with 101 human partners and found consistent results where our approach was able to balance advantage and Pareto optimality well. Subjectively, participants thought that our model was one of the most fair and effective and would like to be represented by it during a negotiation in the future. Overall, our approach balances both desiderata the best against both simulated and human partners. For further analysis and experiments, please check out our paper. Thank you.